Today I'll be going over your Unit 4 review, the no calculator portion. First question, draw a possible graph where all of the values of x, if f prime is less than 0 and f double prime is greater than 0. Well, if the first derivative is always negative, then our graph is always decreasing. And if our second derivative is positive, that means it's always concave up. So lots of different examples that would work, but just decreasing and concave up would look like that. The next one, on the graph of y equals f of x given below, f prime and f double prime are both positive on one interval. So we're looking for the interval where it's increasing, so that's going to be from B to D, and concave up, so that's going to be this portion of the graph right here. Okay, compare the values of f of D, f prime of D, and f double prime of D. Well, f of D is positive. F prime is 0, because the tangent line there would be 0. And then since it's concave down, the second derivative is less than 0 or negative, which means f double prime of D is less than f prime of D, which is less than f of D. What can be determined about the function at the point x of a if f prime of a is 0? Well, the first thing I know is that a has to be a critical point. If the first derivative is 0, it is a critical point. The second thing I can say for sure is that the slope of a tangent line at that spot would be 0. Okay, so now we're going to write the equation for the tangent line to the graph of this at its inflection point. So first we need to locate the inflection point. I'll take the first derivative, which is going to be 3x squared minus 2x. The second derivative will be 6x minus 2, which means 2 equals 6x. So our x is going to be 2/6 or 1/3. So that's our location. So then I need to find my point and my slope. We'll find the point by plugging 1/3 in to our original function. So this will be 1/27 minus 1/9. If I get a common denominator by multiplying by this 3/3, the y value will be a negative 2/27. For my slope, we'll plug our 1/3 into the first derivative. So this is going to be 1/9 times 3, so 3/9 minus 2/3. So it's really 1/3 minus 2/3, which is a negative 1/3. Okay, so y plus 2/27 equals negative 1/3 x minus 1/3 would be the equation for my tangent line. Okay, so we're given a graph. Okay, this time the graph is of the second derivative. So for what points does x have points of inflection? Well, that's going to be any time where the concavity changes, which is when f double prime changes sign. So here it goes from positive to negative, here from negative to positive. So at A and at C, we will have points of inflection. Okay, here we're given the graph of f prime from -6 to 6, so we'll kind of ignore the extra stuff. So we want to find the point 3, 2 is on the graph of f of x. Write an equation for the tangent line at 3, 2. Well, we have our point. Our slope we're going to get from this graph. If this is the graph of f prime, this is the slope. So f prime of 3 is 4. So my tangent line would be y minus 2 equals 4 x minus 3. Next, how many points of inflection does the graph have from -6 to 6? So this is where the second derivative changes signs on the graph of f prime. That means we're looking at the slopes. So the graph is decreasing to this point, then it's increasing, then it's decreasing. So anywhere where it switches from increasing to decreasing or decreasing to increasing, we're going to have those inflection points. So there's going to be 2 here and here based on that graph. So let a twice differentiable function for all real values x. And we're going to look at what properties guarantee that we have a relative maximum and what properties guarantee that we have a relative minimum. We have 2 different tests for this. We have the first derivative test and the second derivative test. From the first derivative test, we have a relative maximum if f prime of x switches signs from positive to negative. For the first derivative test, we have a relative minimum if f prime of x switches signs from negative to positive. The second derivative test, we have a maximum if the first derivative is 0 and around there our graph is concave down, or the second derivative is 0 or less than 0. We have a minimum if the first derivative is 0 and these really say c. Okay, if f of c is 0, f prime of c is 0, and the second derivative is positive, meaning we have a concave up graph. Next question says to draw a graph of a differentiable function that has the conclusion of the mean value theorem satisfied 2 times on the interval from -3 to 4. So the mean value theorem says the slope of the secant line equals the slope of the tangent line. So there's lots of different graphs you can do. So my secant line is here, and there's going to be 2 locations where the tangent line is going to match that slope. Okay, the graph of the second derivative is shown. Draw a graph of what could be f of x. Well, from this graph, we can talk about concavity. Okay, so the graph of the second derivative is negative, then positive, then negative. So we have inflection points at -2 and 2. And the graph is concave down, then it's concave up, then it's concave down. So as long as our graph has those characteristics, we're good. So I'm going to do concave down, then maybe concave up to concave down. Okay, the function f of x equals x to the 1/3 on the interval -1 to 1 does not satisfy the hypothesis of the mean value theorem, because if I took the derivative, this is really 1/3 x to the 2/3. So it is not differentiable at 0, which is in the range that we're asked for. Okay, but in this case, it actually does satisfy the mean value theorem. So the mean value theorem is the slope of the secant line equals the slope of the tangent line. So the slope of the secant line, we're going to have 1 to the 1/3 minus -1 to the 1/3 over 2. This will be 1 minus -1 So we have 2 over 2, which is 1. So we're looking for where the slope of the tangent line also equals that. We've already found the derivative here. Okay, so if this is true, then 3x to the 2/3 needs to equal 1, which means x to the 2/3 equals 1/3. Okay, I'm going to cube both sides of this, so x squared equals 1 over 27. Okay, which means x is going to be plus or minus the square root of 1 over 27. So there's actually 2 answers. You do want to check that they're in the open interval. So if we'd gotten like 1 or -1 as the answer here, that wouldn't satisfy it. But those 2 do. All right, the absolute minimum of this function on the closed interval 0 to 2 occurs at x equals, well, we have to find our candidates, and our candidates are going to be the endpoints and the critical points. So for our endpoints, f of 0, if I plug 0 into this, is just going to be 2. F of 2 is going to be 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2. So 8 minus 4 times 6 is 24. 18 plus 2. So 18 plus 2 is 20, so we end up with 28 minus 24, which is 4. Next, we want to look at the critical points. So we'll take the derivative. And then factor. So we're going to have x minus 1 and x minus 3. So either x equals 1 or x equals 3. 3 is not between 0 and 2, but 1 is. That's going to be 1 cubed minus 6 plus 9 plus 2. So we'll have 10, 12 minus 6 is 6. So our 3 candidates are 2, 4, and 6. 6 is the maximum. But we want to look at what the question's asking. It says it occurs at x equals, so we're looking for the x value. So our solution there is that x equals 1. The next one is similar. We're going to find the minimum value. So this time we actually want the value of the acceleration between 0 and 5 obtained by the particle's velocity is given by this. So first we have to find our equation for acceleration. Okay, again, we want to look at our critical points and endpoints. So we're going to find a of 0 is going to be 24. A of 5 is going to be 3 times 5 squared minus 18 times 5 plus 24. So these numbers kind of get big, but we can handle it. This will be 25 times 3 is 75. 18 times 5, well 18 times 10 would be 180, so half of that would be 90, just a little trick. Okay, so this ends up being 99 minus 90 is 9. Then we want to look at our critical points. So a prime of t is going to be 6t minus 18. Set that equal to 0. And we get that t is 3. So then we want to plug in 3 into our acceleration. Wrong equation. So we get 3 times 3 squared, which is going to be 27. This is going to be minus 54 plus 24. So we end up getting negative 3 out of this. So the minimum value is going to be negative 3 of these 3 candidates. Okay, so the derivative is given by negative x squared, x plus 3, x minus 2. So what are the critical points? The critical points are going to be 0, negative 3, and 2, anything that makes the derivative 0. Then we're going to find the relative mins and maxes. So I'm going to do this with number line charts. So our 3 critical points are negative 3, 0, and 2. Then we look at each one. So the first one here, negative x squared, is negative for all values except 0. This one will go from negative to positive. This one will go from negative to positive. So my derivative, we've got a negative times a negative times a negative, which will be negative. Negative times a positive, gives me a positive, and this will be negative. So we're decreasing, then we're increasing, then we're increasing, then we're decreasing. So on my number line chart, I have a minimum here and a maximum right there. Okay, so where do we have a relative maximum? At x equals 2. Our relative minimum at x equals negative 3. And then we want to make sure to justify our answer. Our justifications from the first derivative test. This is a maximum because f prime switches signs from from positive to negative. This is a minimum because f prime switches from negative to positive. So make sure that you say f prime. If you say something like it, then you're going to lose points there. All right. So this is looking a whole lot like L'Hopital's rule. So what we're going to do is check to see what's happening at the top and the bottom. So the limit as x goes to 0 of 4x squared when we plug in 0 is 0. The denominator, e to the 4x minus 4x minus 1. So e to the 0 is going to be 1. This will be 0. This will be 1. So we do, in fact, get 0. If the limit of both the top and the bottom are 0, then we can apply L'Hopital's rule. So I'll do the derivative of the top, the derivative of the bottom. This is going to be e to the 4x times 4 minus 4. But again, if we plug in zeros of 8x is going to be 0, and the denominator okay, if we plug a 0 in here, that's going to be 1, and we get 4 minus 4, which is 0. So we've got to do this again. Now remember, you need to include each of these limits. So this is going to be 8 over 16e to the 4x, which now we are good to go. So I'm going to plug in 0, which means I'm going to have 8 over 16, or 1/2. This one's going to be pretty similar. Okay, of e to the x minus cosine x minus 2x. So as we go to 0, this will be 0, this will be 1, and this will be 1. So we'll have 1 minus 0, which is 0. Okay, and this pretty obviously is also 0. So we're going to take the derivative. So we'll have e to the x Derivative of cosine is negative sine, so this will be plus sine x minus 2. Over 2x minus 2. Okay, now if I plug in 0, we're going to be fine. So we're going to have e to the 0 plus sine of 0 minus 2 over 2 times 0 minus 2. E to the 0 is 1, sine of 0 is 0, minus 2. In the denominator I have minus 2, so we end up with a negative 1 over a negative 2, which is a positive 1/2. So here, again, we have the graph of f prime on the interval negative 4 to 2. So you should probably kind of like extend a little bit. Not that that'll affect our answers. So we're going to have some questions. We're going to figure out where it's increasing, maxes and mins, concavity. So what I'm going to do is I'm going to do a number line chart. I'm going to take this graph and turn it into a number line chart because it's easier, I think, to look at the number line chart rather than the graph. So first I want our critical points, which is where the derivative is 0. So I'll put my endpoints and my critical points at -3, -1, and 1. Our derivative is 0 there. Surrounding it, the derivative is positive here. It's negative here. Then it's positive. Then it's negative. So my graph that we don't have in front of us is increasing, decreasing, increasing, then decreasing. So we have a maximum here, we have a minimum here, and a maximum here. So the first question says, where is the graph increasing? So it's going to be increasing from -4 to -3, and then again from -1 to 1. My justification is simply f prime of x is greater than 0. Okay, the maximums and the minimums. I have maximums here and here because the derivative goes from positive to negative, and we have a minimum here when x prime goes from negative to positive. So put that in writing, relative max at x equals -3 and x equals 1 because f prime changes sign from positive to negative, and a relative min at x equals -1 because f prime changes sign from negative to positive. Next we're looking at concavity. So going back to my graph, okay, we have our endpoints. Okay, we're looking at the derivative of this graph. So in this graph is has a slope of 0, which is at -2 and 0. Since we have a slope of 0, the derivative would be 0. And then if the graph is decreasing, we have a negative derivative. If the graph is increasing, we have a positive derivative. So this is concavity. This graph is concave down, concave up, concave down. So for our intervals where our graph is concave down is from -4 to -2 and 0 to 2. And our justification is f double prime of x is less than 0. Okay, next we want to sketch a possible graph. If -3 is 4, 1, 2, 3, 4. The last part of this problem is to graph. So if f of -3 is 4, okay, so let's bring our information back here. -3 is going to be a maximum. We have a minimum at -1, so I'm just going to pick a point lower. And then our other maximum's at 1. Okay, and then we have inflection points. And kind of how I like to do this is we have an inflection point at -2, so right in between here. So if I put a dot kind of right in between. And same here with 0. Okay, so we're concave up to this dot, then we're concave down to concave up to concave down. Okay, this graph can look different, but as long as you have your maximums, your minimums, your inflection points, then we're good. So that was your calculus unit for review for the no calculator portion.